Hello, hello, hello. This is Nicholas on this lovely Thursday afternoon, wanting to talk to you today about the Gaussian curve. And now it's something that we see a lot. Typically, it's introduced in a high school class. It's also called the bell curve or the normal distribution, right? It's got a mean usually at 0. It's just a bell that's usually drawn a lot better, and with a standard deviation of 1. And a lot of times, we just kind of don't really talk about the function that defines this curve or where this curve actually comes from. And that's what I want to do today in this video. I want to derive the equation for the bell curve. And really the most that this should take is some Calc 2 integration techniques. Nothing much more than that. So let me begin with a thought experiment on the proof of the Gaussian curve function. So let's say I've got this dartboard here, and we've got this person throwing darts at the dartboard. What would we expect of the distribution of the darts? Well, if assuming they're aiming for the bullseye, which say is right here, the distribution of darts would be radially symmetric, right? If we go a distance r out from the bullseye, we wouldn't expect more darts to be, at least theoretically, above the bullseye than below the bullseye, right? We'd expect an equal number of darts along this circle given by this radius from the bullseye in a theoretical scenario, right? And so what that means is that if we're to talk about the expected number of darts in, say, some tiny area dA of the dartboard, and we're to define a probability density function, call it phi, the number of darts would be phi dA, right? The probability of finding a given dart times the area, or in other words, the density of the darts times the area of the darts. It's kind of like the mass of darts, or in other words, the number of darts, right? So what we can also say then is that phi, this probability density function, is just a function of r only. In other words, phi is radially symmetric. In other words, it doesn't depend on this angle theta right here, right, if we're working in polar. Okay, so now the next thing that I'm going to assume about this dartboard is that the directions are statistically independent of one another. And what that means is that if I'm switching to polar now, right, or I'm sorry, if I'm switching to Cartesian now, x and y, right, if I go a distance x out, that has no impact on the density of darts a distance y up or down. In other words, the x direction does not impact the y's direction density of darts, or vice versa, right? They're independent of one another, and that seems like a reasonable assumption to make, right? And so what I'm going to say is that this is equal to f of x, f of y, dA. Where f is some other probability density function that works just in 1D, which is what we want, right? Because the Gaussian curve is it's a single variable function, right? And also on another note, why am I using this dartboard example? Another way you can think about it, if you're like, well, how in the world would I have thought of a dartboard, is you could imagine instead of what I'm essentially doing with the dartboard, except not really saying it, but now I'm gonna, is what I'm doing is I'm taking this Gaussian curve, right, which lives in 2D, and essentially I'm putting it in 3D, right? And if you imagine this projection on the xy plane, right, I'm essentially taking the curve and spinning it around the z-axis to get this surface. And what I'm really working with in this dartboard case is the Gaussian curve surface, right? So it's all of its cross sections in the x, y, z space are these Gaussian curves, right? And it's got this radial symmetry to it. Okay, so now what I can say is, well, I can cancel out these dAs, and r in polar, right, is just phi of the square root of x squared plus y squared. And now let's try to do something with getting rid of this phi, because we don't want to work with the phi, we want to work with the f. So one thing I can do is letting y be equal to 0, right, I'd get f of 0, f of x, is equal to phi of x. And technically, it's the absolute value of x, but since there's this radial symmetry, we don't really have to worry about the absolute values, right? It's half on one side, half the area on one side, half the area on the other. So we don't really have to worry about the absolute value. Okay, so f of 0, right, that's just some probability. That's just some scalar, which I'll call lambda. So what we get is that lambda times f of x is phi of x. And if I did the exact same thing by letting x be equal to 0, I'd get lambda times f of y is equal to phi of y. And so in other words, lambda and phi, you know, when I get rid of this extra dimension, what I find is that lambda and phi are just scalar multiples of one another, which is kind of a neat fact, right? They're just off by some constant. So what I can do now is write that, given the fact that they're both scalar multiples, I can write that f of x times f of y is just some scalar multiple of phi, which is a scalar multiple of f's, which is the square root of x squared plus y squared. In other words, I can just replace phi of whatever by lambda times f of that same whatever, right? I can replace, since I have this relation, phi of x is equal to lambda times f of x, I just replace x with the square root of x squared plus y squared. Okay, now just some algebra. Whoops. F of x, dividing all this through by lambda squared, I get f of x over lambda times f of y over lambda is equal to f of the square root of x squared plus y squared over lambda. And this hopefully makes it readily apparent what variable change I should use, right? I should let g of x be equal to f of x over lambda. And then I get g of x, g of y is equal to g of the square root of x squared plus y squared. Okay, now we have reduced this Gaussian curve, essentially, to finding functions that satisfy this relation here. And what type of functions would do that? Well, as it turns out, it's functions of the form g of x is equal to call it lambda e to the ax squared, right? G of y would be lambda e to the ay squared, and g of the square root of x squared plus y squared would be lambda e to the a times the square root of x squared plus y squared. And so if I multiply g of x and g of y, I'd get, it's a lambda squared. The scalar doesn't really matter out front though. E to the a times x squared plus y squared. But what I forgot is that since it's the variable is already being squared, there's no square root right here. My bad. Times x squared plus y squared. Because both of those variables are already being squared. And so they cancel out with the square root. So, and the lambda squared right here really doesn't matter. In other words, we're just saying it's some scalar multiple, right? So this type of function here satisfies this relation. And now you might be saying like, well, what about, for example, if I use a different base other than e, like 2 to the x squared, right? 2 to the x squared times 2 to the y squared is 2 to the x squared plus y squared, right? And yes, it is. And that satisfies that relation, right? The square root of g of the square root of x squared plus y squared. But any base, we like to work, I mean, e is a nice base, right? So we can turn that base 2 into a base e just by noting that 2 is equal to e to the natural log of 2. And natural log of 2 we can just call some constant a. So 2 to the x squared plus y squared is e to the a times x squared plus y squared. In that particular case where a is natural log 2, but you could have used whatever other base you wanted. And so that's why we tack on the constant a, and again we tack on the constant lambda, just by noting that g of x times g of y is just some scalar multiple of g of x squared plus y squared. So the most general case has a lambda out front. Okay. So our solution g of x is lambda e to the ax squared. And now basically what we're left with is finding lambda and a in terms of parameters of the normal distribution. Namely, the normal distribution is characterized by two parameters, right? That's mean mu and its standard deviation sigma, or variance sigma squared. Okay, so something that will help us with finding what a would be is the normalization condition, right? The fact that the area under this whole curve has to be 1. And so hopefully you're smelling the calc 2 that's about to come already. So basically what we're going to require is that the integral from negative infinity to infinity of our function g of x be equal to 1 because it's a probability density function. And then also we're going to let a be negative h squared, for example. The reason for that being that lambda e to the ax squared, right, that depending on your value of a, if a is negative, everything is dandy, but if a is positive, then we just go up and up and up, right? So in other words, we want a to be only negative so that when x tends to plus or minus infinity, g of x tends to 0. And so we get a finite area by letting this substitution happen. Okay, so we have the integral from negative infinity to infinity of lambda e to the negative h squared x squared dx. And now this is just kind of some routine calculus. We're going to let u be equal to hx, and we're going to still get the integral from negative infinity to infinity. And then we get lambda over h e to the negative u squared du. And now this is a special type of integral which I know I have solved on my channel. And if I haven't, I have definitely done videos on the material that you need to solve it, namely the Jacobian matrix, which I have like 3 videos on. So I'm not going to go through the steps of solving this integral. It turns out to be lambda over h times the square root of pi, that integral, what it evaluates to. And that's equal to 1, right? So in other words, lambda is or I'm sorry, not lambda. Let me solve for h. H is negative pi lambda squared. Or h squared. H squared is negative pi lambda squared, because we want to solve for h squared because that's what it is in the function right here, h squared. Okay, so now what we have is that g of x is lambda e to the negative pi lambda squared x squared. So we're getting there, right? We just need to find lambda in terms of some parameter of the normal distribution, right? The mean really isn't going to give us much of anything, but we can use the standard deviation and we can use the variance formula, right? So one thing that I'll note is that the variance of x of your distribution is the square of the standard deviation, just by definition, which is equal to the integral from negative infinity to infinity of x squared times the probability density function g of x dx. That's just a formula from statistics. Okay, so we can use that formula to write lambda in terms of sigma squared. So we get that sigma squared is the integral from negative infinity to infinity of, let's see, so we get, I'll put the lambda out front and I'll make it x times x e to the negative pi lambda squared x squared dx. So I split up the x's and I pulled the lambda out front. Now what I can do is integration by parts. So that's why whenever you got a polynomial times some random function, you want to differentiate the polynomial integrate this. And I had an x squared here, so I needed an x in order to integrate this whole thing here, right? And I'm going to differentiate the x. So when I do integration by parts, I get lambda times negative x over 2 pi lambda squared e to the negative pi lambda squared x squared, evaluated from negative infinity to infinity, plus the integral from negative infinity to infinity of 1 over 2 pi lambda squared e to the negative pi lambda squared x squared. And you can check my math on the integration by parts. I don't believe I messed up anywhere. Okay, so now notice that this first part goes to 0 because x squared, this is always negative, and we're always going to have a positive here, so it's e to the negative something, and that will go to 0 in both cases. And then so now really what we get is that sigma squared is equal to lambda times the integral from negative infinity to infinity of 1 over 2 pi lambda squared e to the negative pi lambda squared x squared dx. Okay, now this might look frightening, right? But realize that we already established the normalization condition. And so our function g of x is really lambda e to the negative pi lambda squared x squared. And if I bring this out front, this 1 over 2 pi lambda squared, and I bring the lambda back in, right? What do I get? I get 1 over 2 pi squared times lambda, 1 over 2 pi lambda squared, integral from negative infinity to infinity of lambda e to the negative pi lambda squared x squared dx. And this integral right here, we just forced our function such that that integral from negative infinity to infinity is 1. In other words, it's a normalized curve. And so we get that sigma squared. If this whole thing is just 1, we get that sigma squared is 1 over 2 pi lambda squared, right? And then that implies that lambda is 1 over sigma square root 2 pi. And so all in all, putting it together, g of x is 1 over sigma square root 2 pi e to the negative x squared over 2 sigma squared, right? And in all technicality, the most general type of function, g of x, would, I'll just write it up here, would technically, this is assuming that the mean mu is centered at the origin of your coordinate system on the x-axis. In other words, that the mean mu is 0. If we were to shift it to include some arbitrary mean mu, then it would become a negative x minus mu squared. And that is the equation for the Gaussian curve. And it might look a little scary, but if we do the standard things like let the mean be 0 and let the standard deviation be 1, then it simplifies quite nicely. We have g of x is 1 over square root 2 pi e to the negative x squared over 2. And that's really not that bad. And so I believe with all that,